Hey guys, this lesson is called scatter plots, and that's exactly what we'll be doing today. Again, this might not seem very interesting at first, but these plots hold so much significance in our lives. It's actually kind of crazy, because this is a graphical way of representing data, right? But it's actually really significant. So, but the basics first, right? So here we have age in years for our x-axis and height in inches. And you can see that there's kind of a correlation, right? As you get older, it seems, the heights tend to be getting bigger and bigger. People tend to get taller as they grow older, especially between the ages of 8 and 14. So that seems to check out, right? And there seems to be some, few that are straggling a bit. But there seems to be a clear positive correlation, right, between age and height. When I say positive correlation, I mean as one gets more positive, the other one also gets more positive. That's what I mean. So, what we could do, and what a lot of people do, is try to draw a line of best fit through this. What that means, and there's actually a mathematical way of going about this, but it's pretty complicated, so you can just eyeball it in some cases and get pretty close. So you just kind of want to go through what looks to be like the average of all these, right? So if I was going to draw a line, I'd be like, okay, it starts like somewhere over here, there's like, it's not a dot, there's some points up and down here, so maybe we could go in the middle. And then it seems to be like just going right along there is where the majority of the dots are. You're trying to get it to be like where most of the dots are. So I would go from here and I'd aim for like right, that's not straight, that's fine. Right there is where I'd probably try to draw the line. And this line, this isn't representing really any of the dots, right? Some of them may be on the line or pretty close to the line, but some of them are way off. And what this line just represents is if we had to draw a line through this to kind of represent like the average or the line that can represent most of the data accurately to see what the trend is, right? Because as people age more, they grow more, right? So this is a positive line through these. This is about where I'd put that line. Might be a little lower because of all these dots right here. But, it's okay. We can eyeball it. But this next clip that we're going to do, that I'm going to show you, is so relevant and so important. And this is where it actually gets into the real world kind of stuff. So, yeah. Alright, so what we're going to talk about now is called Simpson's paradox. And it's not really, that much of a paradox. It's more of just looking at subsets of data, smaller sizes of the whole data versus all of the data. So ignore all this for now. We're going to talk about it soon. Just look at this basketball success versus height graph. Okay. So basketball success, is obviously relative. It's like basically how good you are in comparison with others with basketball. So here we are. We have some scatter plots, and I've drawn lines through them. So, height, as you get taller, we're trying to figure out, does your basketball success go up, go down? Does it have no correlation, So, here are people from ages 5 to 10. So they're saying, as we get taller, you tend to have more success in basketball, right? In comparison with the rest of your peers there. But then here we're getting taller, but you're still, there's basketball success, but not as much in comparison when you're like 20 to 25, right? There's some pretty good short people too. But there's still some kind of a correlation there, right? Just not as much here, because their basketball success is lower. Same thing with this one from ages 40 to 45. You're getting taller, you seem to have more success, but less success than when you were 10 in comparison to with the rest of your, 42-year-olds on the basketball team. So, you could look at it like this. You can look at each section, say, well, with ages 5 through 10, you're getting, they're not as tall as these people, but you're getting more success with that same age group, right? With here, you could say the same thing. They're getting taller, there's more success. Here's the same thing. They're getting taller, there's more success. But as you go down the age groups, there seems to be less and less success with height each way. So you could say, well, actually height doesn't matter when you're playing basketball, because there's a negative correlation between all that stuff, right? So that's the kind of paradox of it. If you took all of these, just the separate subgroups, all of the lines of best fit would be going up, right? You would say, oh yeah, there is a correlation between height and how good you are at basketball. But if you took all of this data, right, if I was just showing you this graph, what would you do? Would you go like that, or would you go like that? So that's kind of the question. And this actually happens in real life. And this is why it's so important. So now we're going to move on to this. And I have to thank Ryan Arnold and Tim Erbrich for letting me use, this isn't actually their graph, but I looked at their presentation that they did for this last year to help me with this. So yeah, thank you, Ryan and Tim. And we'll cite whatever sources they used in our little description. But yeah, so UC Berkeley, I think in the 70s, had a study that showed that less female applicants were being admitted than male applicants. Okay? By like a significant percent, by like 10%. So like 40% of male applicants were being accepted, and like 30 or something percent of women applicants were being admitted. Those aren't the exact numbers, just as these aren't the exact numbers, but this is just the trend. So there's a huge scandal. They're like, this is the 70s, everyone's cool with women now. They're like, you gotta admit the same amount of women. So this is what they found. They did another study. They looked at the numbers. This x-axis is the percentage of women applicants, okay? This y-axis is the percentage of male applicants. And all of these boxes are different departments at Berkeley that you could apply to, right? The bigger box, don't worry about these huge boxes yet. Just these boxes inside the box. Those are the departments. And the bigger these boxes are, right? This one's bigger than that one. The bigger they are is just the bigger the department is, right? Now, this big box over here has higher admission rates than this big box over here. Okay? And most of the people applying here are males, right? There's like 90% or like, you know, around 50 to 90% here, and around like 0 to 40% here for women. So like over 50% male applicants, less than 50% women applicants, and they have higher admission rates. So that means more males are going to be going to be let in because more males are applying and more people are being let in general. That makes sense. And over here, this box has lower admission rates, but there's more women applying to them. So if they have more women and less men applying to them, then they're still going to get more women being accepted just because of, you know, more women are applying. But overall, these have much lower admission rates. So there's going to be just less women in general, even though that there's going to be more men. Sorry, more women getting accepted, but because there's such lower admission rates, there's just less women accepted in general because everyone's being accepted less. And this kind of perfectly shows how that data got to be, right? If there is more males admitted, it's because that they're applying to departments that have higher admission rates. And less women admitted because they're applying to departments that have lower admission rates. So you have to look at each subsection of the data to see what's actually happening here, if that makes sense at all. So this example was kind of like, okay, do you look at all the data or the subsections? And it would kind of make more sense to look at the subsections here, right? But here you got to go into the nitty-gritty and see how each individual trend looks, because you can't just look at the whole thing and make a conclusion. And that's one way that people can lie with statistics so easily, right? I mean, there's like a million examples of people lying with statistics, and that's also why it's so dangerous just to look at a statistic and like use it all the time, because people can lie and misrepresent data literally all the time. I'm going to just pull up another example. Apparently, some time ago, Colgate was saying that their brand of toothpaste was being preferred by like 80% of dentists or something. And the ad suggested that they are being preferred over other toothpaste brands, right? 80% of dentists preferred them over other toothpaste brands. But the only data that people could find was that dentists preferred them and a bunch of other brands over some other toothpaste brands, right? So it could be that, yeah, they like really liked Colgate, but also a bunch of other stuff. Or it could be that those other brands were just like absolutely horrible and they preferred Colgate with a bunch of other toothpaste brands, which could be just as good or even better than Colgate. So that's pretty misleading, right? Another example could be you have a super small data set and say like, well, 60% of dentists prefer our thing, or 60% of whatever prefer our brand. But if you only surveyed like 20 dentists or 20 experts or whatever, and only 12 like your thing, that's also pretty misleading, because that's a really small data set, right? You have to get a bunch of people to make sure that 60% or however many percent really like your thing. The same could be true for like only 4 out of 5 people like your thing, right? You have to get a lot more data to make sure that that's an actual 80% of people like your thing, because you could have chosen any random 5 people and 4 of them could have liked your thing. But maybe if you got 20 more people in, maybe those were the only 4 people who liked your brand, right? So having large data sets and actually taking time to view the data set as a whole and then also looking at the subsections and see how they compare is so important. So that's why this lesson is actually super relevant, and there are a bunch of other ways that you can lie with stats, but yeah, that's kind of a main one. So thank you.